Many years ago, I derived these two equations as a proof to make sure they actually work. And it was a hassle and it took forever. It was very difficult. And I've done it once or twice since then. And I'm going to do it once more for life, record it, and I'm done. And I did not check my work on here tonight, so if there are mistakes, I'll leave you to track them down and find them. And I'm going to do one shot, and if I have mistakes, I'm going to leave them. Okay, these two equations here we use when there's a perfectly elastic collision between two masses in a straight line. But these two equations only work in a special case. And that is when you have one mass hitting a second one, and the second mass is starting at zero. Now, it doesn't matter what the units are, zero is zero. The equations here describe the velocities of the two masses after the collision. This is the first mass that's coming in, and this is the second mass that's sitting still before it starts. And these equations will tell you the velocities after the collision when we know the velocity of this ball when it's starting, and this ball, the second ball is zero. Now, it is important to note, and this is what makes this possible, that in possible to come up with these, that in perfectly elastic collisions, the momentum is conserved, but also kinetic energy is conserved. And so, basically, you set up two equations with a bunch of unknowns. I will show you how to get these equations on the following pages. I don't like it when the equations just fall out of the sky and say, oh, here, use this when it just works. We have to be able to show and prove how we come up with it and why it works, and that's what I'm going to do here. Okay, now, on a side note, pretty much, a Newton's cradle, one of these guys, works because of this phenomenon in these two equations. This Newton's cradle is a practical representation of these two equations in action. Also, you've got simultaneously the conservation of both kinetic and energy and momentum. When these are both conserved simultaneously, the height and number of balls dropped on one side must be matched exactly coming out on the other side. Now, also, with the Newton's cradle, it's kind of a special case because all of these balls are the same mass, and the ones that affect it if you drop one is the one on this other end. Momentum's just transferred through the ones in the middle. This isn't a lesson on Newton's cradle, so I'm not going to talk about that any further. You could do a whole bunch of things with that. Okay, so we have two equations. Kinetic energy has to be conserved. The kinetic energy of the first ball before the collision combined with the kinetic energy of the second ball before the collision has to equal the kinetic energy of those two balls after the collision. Now in our case, in our special case, this one is zero because the second ball isn't moving anywhere. Also, momentum is conserved. The momentum of the first ball before the collision plus the momentum of the second ball before the collision has to equal the momentum of the two after the collision. And again, the momentum of the second ball is zero starting out. I'm not going to bother to prove these because that's been done repeatedly by many people. We're going to accept those. Okay, so now the rest of it is just manipulating equations to make this work. And this takes a while and a lot of paper and a lot of effort, and a lot of substitutions. So there's the conservation of kinetic energy, conservation of momentum. We have two equations, and at most we can only have two unknowns at a time. Okay, so let's look at the kinetic energy side. I can get rid of all the halves, and I can move this m1 v1 prime after the collision squared over here, and the m2 v2 squared over here, get this equation. And then reorganize, take the m1 out, and I have v1 squared minus v1 prime squared equals m2 times the quantity v2 prime squared minus v2 squared. Okay. Now, on this side, okay, now let's go ahead. I'm also rearranging this by pulling m1 v1 prime over here and taking m2 v2 over here. And I can also pull out the m1 and m2. I know that I need m's in my final equation, so I'm trying to isolate those at this point. Now, you got to be creative. You're here. Oh my gosh, what are you going to do? So you have to come up. You have to have an aha moment and realize, oh, these are binomials. I can expand those. You thought you'd never expand a binomial in real life, here it is. And once you expand that binomial, this part is here. Yeah, here. This part is here. So I now have two equations that I can divide by these h's. So I'm going to take this equation A over here. See, I moved it over here, put it underneath, divide it. And I'm left with v1 minus v1 prime equals v2 prime minus v2. Now, if I rearrange that by taking v2 over here and v1 over here, we get an important result. That tells us that whatever the difference in the velocities were before the collision, as long as the collision is perfectly elastic, has to equal the difference between the velocities after the collisions for any masses, regardless of masses, and regardless of the starting velocities. I mean, it could actually be moving on this one. And furthermore, if v2 is 0, you can't, here, I get rid of this. I'll just do it this way. If v2 is 0, if this guy is 0, then v1 is equal to v2 prime minus v1 prime. Not sure how, I might have made a mistake there. Let me see here. No, I take this to the other, I just said the wrong thing. Take this to the other side. v2 prime is equal to these two added together. That is going to come in handy. We're going to call that equation C. We're going to use it later. Yeah, so there's a lot of labeling, a lot of stuff for later. Now, on the momentum side, I got one more little thing I want to clear up here. Once I take these to the other side, I know in my equations I end up with m's in numerators and denominators. So I am going to take m2 over here and take v1 minus v1 prime over here and save this equation for later. We're going to be able to use it. Okay, so now on to the second page. I got to start getting these to, equations. It's going to take a while. Okay, so if I take equation C and equation B and start putting them together, remember if v2 is equal to 0, I can just take this out and I've got a new equation. I'm going to be able to use this one later, so I'm going to write it down as D. If I substitute v1 plus v1 prime in for v2 prime, I've got this. Okay, now it's starting to look a little bit more like the equations we have. All right, if I bring this v1 minus v1 prime up here, this is what I have. And if I rearrange by putting v1 over here, now what I do? v1 prime over here, and then switch the whole thing around. So I took the v1 prime over here, and then I switch both sides. This is what I get. Now it's starting to look pretty close to what I've got. I can't do any more with this until I get a common denominator. So I'm going to use a common denominator of m sub 2, put that in there, and now you can cancel. Let's see here. What would I cancel? How would this cancel? I was going to do this on the fly. And this minus that. No. Been at this too long. Cancel all the m2s. And then we can just use the numerators. There we go. So our numerators are equal to one another. Now it's just a matter of rearranging, and we're there. Get rid of this. I'm done with it. On the next page, just rearrange, put my m's together. Oh, this is looking better because, just rearrange, get my m's together. Divide by m1 plus m2 on both sides, leave the negative over here. Now, when I take the negative to the other side, what that effectively does is switches my m1. m2 minus m1 becomes m1 minus m2. And I've got the equation from the first page. Ta-da! Wasn't that easy? No, it took me many, many tries and many, many hours and many, many years. It's this equation. I think we can get rid of... So this first equation, this is the first equation from the first page. page that describes the speed of the incident ball after collision. I can get rid of these two. I'm going to go to the next page and find this equation. So equations that I've already come up with, I'm going to go fetch them here. So I'm going to start with equation D from page 4, which is this one. And I'm going to rearrange it by putting V1 minus V1 prime up here equals V2 prime. There was an equation C from a few pages ago that all these were valid. V2 prime is equal to V1 minus V1 prime. Let's substitute. I got to rearrange that one down here. And then I substituted in for V1. See, V1's here. V1's here. I put this part in. It's in black there. Okay. Then I expand all that and get my M's up there and get some like terms or get some terms. I've got two M1 V1s. Now things are looking optimistic because I know there's a 2 M1 V1 in that equation. Okay. And I bring this to the other side. Take my V2 prime out. And V2 prime, take this under there. There's my other equation. And ta-da, I am never doing this again. I know I say that about a lot of things, and I do them again eventually. I ain't ever doing this one again. So have a good day.